Hi everyone, my name is Jinghao Huang, a PhD student from George Mason University in Dr. Chao Luo's research group. My present topic is about the halogenated carboxylates as organic anodes for stable and sustainable sodium-ion batteries. First, let's talk about some background. The reason why people are interested in sodium-ion batteries as an alternative of commercialized lithium-ion batteries is that the content of sodium is much higher than that of lithium in Earth. Because of its abundance, sodium ion has the advantage of lower cost and higher sustainability to be utilized. As for the electrode materials, compared with the inorganic counterparts, organic electrode materials are lighter, cheaper, and also more abundant. Talking about the organic anodes, currently for sodium-ion batteries, there are 5 organic reaction mechanisms, who are carbonyl, imine, azo, thioketone, and thioester, and anion insertion reactions. Among these five different types of reactions, we are now focusing on the carbonyl reactions. To be more specific, carboxylate groups. The reason why we choose that is that the carboxylate groups can provide a low redox reaction potential below 1 voltage, which is an advantage as an anode material. So in our study, we designed 3 different halogenated terephthalic disodium salts, which are DFTP sodium, substituted by 2-fluorine, DCTP sodium, substituted by 2-chloride, and DBTP sodium, substituted by 2-bromide. In addition, we also prepared the unsubstituted terephthalic disodium salt, which has been reported by the previous literature as a comparison. We expect that all of the compounds will go over the carbonyl reaction mechanism. So after the synthesis of all materials, we did characterizations on them in order to verify their identities. Let me just use DFTP sodium as an example. The first we use FTIR and Raman to identify its key functional group, which is carboxylate group. So from the FTIR spectra, the peak at about 1700 represents the carboxylate group, and also in the Raman spectra, the 2 peaks at 1400 and 1600 represents the symmetrical and asymmetrical vibrations of carboxylate carbon, which can also prove the existence of carboxylate group in DFTP sodium molecule. And the XRD spectra provides clear peaks, which means the product has crystal structure, which can also be proved by the SEM image. You can see in the SEM image, it clearly shows that DFTP sodium has the shape of small rods. And finally, we determine its structure by proton and carbon NMR. From proton NMR, the peak at 4.85 represents the solvents D2O. So only the peak from 7.35 is from the compound. So it represents the symmetrical proton in the benzene ring, of the compound, and from the carbon NMR, the two peaks at 153 and 156 represents the carbon connected with fluorine. The reason why there are two peaks is because of the carbon-fluorine splitting, which also proves the existence of carbon-fluorine bond in the compound. So then we did some electrochemical tests of the all of the four compounds to compare them. The electrolyte we use is 1 mole sodium hexafluorophosphate in DGDME. So from the charge discharge and the cycle life curves, we can obviously find that the DFTP sodium has the best electrochemical performance. It delivers the highest specific capacity, about 220 milliamperes per gram, and it has the best cycling stability. Over 300 cycles, the capacity retention of it is over 80%, while the other three had the obvious capacity decay in 100 or 200 cycles. Then we also did the rate test of the three halogenated compounds. Similarly, it is obvious that the DFTP sodium has the best rate capability and the highest capacity recovery. So we recognize that the DFTP sodium is the best compound among them. So we did some further tests to the DFTP sodium. For example, we did the CV test. The anodic and cathodic peak corresponds to the charge and discharge plateau in the charge discharge curve, and we performed a high rate test at current density of 1000 milliamperes per gram, and found that the DFTP sodium can stably run in 1000 cycles. Then we did reaction kinetics test of the DFTP sodium material, and based on the CV test in different scan rates, we established we established the curves of its anodic peak and cathodic peak based on the natural log of current versus the natural log of their scan rates. So the slope of these two curves is close to 1, which means the redox reaction of the DFTP sodium is dominated by the pseudo-capacitive behavior. And then from the result of EIS test, we found that the interfacial resistance of the electrode stabilized at 18 ohms after 50 cycles. So from the GITT test, we also found that the overpotential of this material is as low as 33 millivolts, which also proves it, which is a very good data. So based on the results of all of the reaction kinetics tests, we finally they explained that the reaction kinetics of DFTP sodium is very good. To study their stability, we studied their SCI layer by XPS test from the carbon 1s from the result of carbon 1s. we found that after 10 cycles, there are carbon fluorine peaks appears in all of the 3 compounds, which means the occurrence of organic fluoride uh, components. So we tested their F1S test and found the proportion of sodium fluoride is highest in the SAI layer of DFTP sodium, and since sodium fluoride is a very strong uh, is a very strong content in SAI layer, which explains what that means the DFTP sodium has the strongest SAI layer, and it explains why it has the highest stability. Then we also did multiple tests to study the high stability of DFTP sodium, such as TEM, XC2 FTIR, and XRD, and SCM tests. So from the TEM test, we have found after 10 cycles, the morphology change of DFTP sodium is smallest compared with the other 2 compounds. And from XC2 FTIR and XRD, we found that the functional groups and the crystal structure of the DFTP sodium has no change after 20 cycles. And also from the SCM images, we can find that from the pristine first cycle, fifth cycle, and 10th cycle, the shape of the shape of the crystalline of DFTP sodium has also no change. So which they all proves that the DFTP sodium has very good stability, and it is better than the other 2 halogenated materials. Then, to prove our expectation that the compounds go over the carbonyl redox reaction mechanism, we did the XC2 Raman and XRD test of different potential stages. So from the spectra of Raman, the 2 peaks of 1400 and 1600 represents the carbonyl group, and they just disappears when the battery was discharged to the 2.1 voltage, and they recovered when the battery when the cell charges back to 2 volts, which means it was the carboxylate group who had the redox reaction during the charge discharge process. And also from the XC to XRD, when the cell discharged to 0.1 volts, it has a large change, which means when it was totally discharged, the crystal structure has a large change, which means which can also prove its mechanism. So both of the XC2 Raman and XRD tests indicates the change of carboxylate groups and the crystal structure of DFT sodium, and they proved its reaction mechanism. So in conclusion, we proved that the DFTP sodium has high capacity, good rate capability, and high cyclic stability. So it can be a promising anode material for the future sodium-ion batteries. And from the experimental studies, we also proved that the DFTP sodium goes for the carboxylate, goes for the carbonyl redox reaction mechanism. So for this study, we thank for all of our supporters, National Science Foundation, the Quantum Science Center and the College of Science from George Mason University, and the Argonne National Lab. So thank you all for listening.